So I will start with the associative memory. How associative memory can be, structured using neural networks. So first thing is what associative memory is. Because you have heard of random access memory, read-only memory, cache memory. So these memories, they are basically memories which are addressed with the help of some address. So if you have stored some data in RAM, then you need the address of the location where the data or instruction is saved, and you fetch that data with the help of its address. But associative memory, on the other hand, is not addressed using an address, rather it is a content addressable memory. So structure of associative memory is that it is content addressable, and it will remember the association between the input pattern and the output pattern. And it can remember association of related as well as unrelated items. For example, so far as human mind is concerned, our memory is also associative in nature. Say for example, you meet a person after 5 years. So you recognize his face, and if you search your memory, you will be able to maybe remember the name of the person also associated with that face. So like that, you remember the association between patterns, and say you have heard some song, and if you are hearing that song after a few months or a few years, then maybe you can remember what movie it is from, or on which hero or heroine that song was picturized. So these are the associations between different patterns, and human mind can remember these associations. So associative memory is basically a content addressable structure which memorizes the association between input patterns and output patterns. And whenever we have trained a associative memory, then if we give some input pattern to the associative memory, then it should be able to recall whatever is the associated stored pattern in the memory. So we have to see, how we train this associative memory and how we recall these patterns from the associative memory. So like other neural networks, when we talk about associative memory, then we will train it using input vector and output vector. So the combination of input and output vector forms a pair, and we will take each pair one by one. So we take the first input vector and the associated output vector, find its contribution to the weight matrix. Then we take the next input output vector pair and find the contribution of the next pair to the weight matrix, then next, and so on. So one by one, we will evaluate the contribution of input output vector pair to the weight matrix, and finally we will get the weight matrix which has taken into account all the input output vector pairs. Once you are done with your weight matrix, that means you have gone through the entire training set. Training set basically consists of your input and output vector pairs. So once you have gone through one cycle of the complete training set, then after that, when you give a input pattern at the input, the associative memory should be able to recall the output vector. And even if the input vector is slightly corrupted or incorrect, even then the associative memory should be able to recall the correct output vector. So that is how the system works. So that means first we have to train the network. So when we have to train the network, then it is trained by storing a set of patterns, and these patterns are, say, stored in the form S:(T), where S represents your input vector and T is the corresponding output vector. So associative memory is basically going to, store the association between the input vector and the output vector. And that association is basically in the weight matrix. So once we have determined the weight matrix using the input-output vector pairs one by one, then we can test this associative memory by giving some input pattern to it and by evaluating what the output pattern would be. And the associative memory will have the ability to identify patterns which are incorrect or which have some missing information. So some generalization it is able to do on its own. So now when we talk about associative memory, the associative memory can be auto-associative or hetero-associative. So auto-associative means that the input and the output vectors are same. So we store some patterns in the memory and we give an input pattern, it is able to recall the correct pattern. So that is your auto-associative memory. And hetero-associative is that input and output patterns are different and the memory is able to memorize the association between the different input and output vectors. So Hopfield network is a auto-associative memory. So in a Hopfield network, we have a single layer of neurons. So we have one layer of neurons and output of each neuron is connected to every other neuron in the network. So you can see in this diagram, there are 4 neurons. First neuron is connected to the second neuron as well as to the third neuron and as well as to the fourth neuron. And the weight between first and second neuron is W12, weight between first and third neuron is W13, and weight between first and fourth neuron is W14. Then if you look at second neuron, it is connected to it is connected to first, third and fourth neuron. So weight between second and first neuron is W21, between second and third it is W23, and second and four it is W24. Similarly, third is connected to 1 through W31, it is connected to 2 through W32, and it is connected to 4 through W34. Similarly, fourth is connected to 1 through W41. It is connected to the second neuron also through W42, and it is connected to the third neuron through W43. But if you look at this, the output of a neuron is not connected to itself. What that means is that when we make the weight matrix, W11 is 0. W22 is also 0. There is no W11, W22, W33 or W44. So that means along the diagonal in the weight matrix, we are going to have all zeros. And from where the activation of each neuron is coming, if you look at that, the first neuron is getting input through weight W21 from neuron 2, through weight W31 from neuron 3, and through weight W41 from neuron 4. So what would be the weight matrix? Weight matrix would be W11, W12, W13, W14. Then W21 in the next row, W22, W23 and W24. In the third row it will be W31, 32, 33, 34, and fourth row would be 41, 42, 43, 44. So that means activation for the first neuron will be determined from the first column in the weight matrix, because the first column would have W11 which would be 0, then W21, W31 and W41. Similarly, for second neuron, it will be the second column which will be used to determine the activation, and for the third neuron it would be the third column, and for fourth neuron it would be the fourth column for determining the activation. So now we have to see that how the weight matrix would be determined for a auto-associative memory. So we have to give patterns to the Hopfield network. These input and output patterns would be same. And for a Hopfield network, the patterns which are being given, they should be orthogonal. So when we say that the patterns should be orthogonal, that means that the dot product of the vectors would be 0. So dot product would be determined by multiplying the corresponding components and then adding them up. So what that means is that if you have two vectors A and B having four components, say A1, A2, A3, A4, these are the four components of vector A, and B is B1, B2, B3, B4, then when I say that the dot product of A and B would be 0, that means A1 dot B1 plus A2 dot B2 plus A3 dot B3 plus A4 dot B4 would be 0. So this is how we'll find out that the vectors are orthogonal, and then we determine the contribution of each vector to the weight matrix. So say the first pattern which is used is 1 0 1 0. So if we have this pattern A, which is 1 0 1 0 as the first input pattern, and we have to find out its contribution to the weight matrix, then first step is to convert this binary vector into a bipolar vector. So when I say bipolar vector, it means that plus and minus, both values would be there and zeros would be converted to -1. So bipolar vector for 1 0 1 0 would be 1 minus 1 1 minus 1. And then since the input and the output vector is same, to determine the contribution of this vector to the weight matrix, we have to take transpose of this vector and multiply it with itself. So when we take transpose of this vector, it will be a column vector, and column vector would have values 1 minus 1 1 minus 1, and it is to be multiplied with this row vector, which is 1 minus 1 1 minus 1. So it's a simple matrix multiplication. So you have to multiply this column vector with the first element, that is 1. So that will give you the first column of the weight matrix, which will be 1 minus 1 1 minus 1. Then we have to multiply it with the next element in the row vector, which is -1. So when we multiply the column vector with -1, we get the second column vector of the weight matrix. So that will be -1 1 minus 1 1. Then we multiply this column vector with the third element in the row vector, which is 1. So then we get the third column, which will be 1 minus 1 1 minus 1. And finally we get the fourth column by multiplying this column vector with the fourth element of the row vector, which is -1. So once we multiply -1 with this column vector, we are going to get the fourth column, which will be -1 1 -1 1. So this is the contribution to the weight matrix of the first input pattern. Say the second pattern is 0 1 0 1. Now I have already said that the output of each neuron is connected to every other neuron, but it is not connected back to itself. So W11, W22, W33, W44 will be 0. So that is what is shown in the weight matrix, that all elements along the diagonal are 0. So now we have to calculate the contribution of the second pattern, which is 0 1 0 1. So you can see that the second pattern is orthogonal to A. So I want you people to find out the contribution of second pattern 0 1 0 1 to the weight matrix. So I will give you 5 minutes and in 5 minutes you evaluate the contribution of second pattern to the weight matrix. So you could find out the contribution of the second pattern. Subtraction. Okay, so what is that matrix? Is it different from the earlier matrix? It is same. So the method for finding the contribution of pattern B would remain the same. First we have to convert this binary pattern into bipolar pattern. So bipolar pattern would be -1, -1. So B in the bipolar form would be -1, 1, -1, 1. And then we have to take transpose of this. So that will be this, and we have to multiply it with this. So when we do the multiplication and then subtract 1 from all the elements along the diagonal, we'll get the same weight matrix which we got for pattern A. But then this is the contribution of pattern B to the weight matrix. So then we have to add contribution of both the vectors to find out the weight matrix. So when we add both these weight matrices, then we get this weight matrix W, which is given here, and the first row is having elements 0, -2, 2, -2, then -2, 0, -2, 2, then 2, -2, 0, -2, and -2, 2, -2, 0. So this is the matrix which we have got by adding the contribution to the weight matrix of pattern A and B. Now we can, multiply this weight matrix with any scalar and get some different magnitude also. Like if we multiply all the elements in this weight matrix by 3 by 2, then your weight matrix would have 3's rather than 2's. So if I have to multiply all the elements in this weight matrix by a scalar which is 3 by 2, then the weight matrix would become 0, -3, 3, -3. That would be the first row. Then second row would be -3, 0, -3, 3. Then next it would be 3, -3, 0, -3. Then -3, 3, -3, 0. So this can be the weight matrix. So say all the elements in the weight matrix are multiplied by 3 by 2 and we get this weight matrix. So if this is the weight matrix, then we have to apply some threshold function also to find out the output vector when an input vector is applied. So say the threshold function that is used is as given, that the function ft will be 1 if t is greater than equal to theta, where theta is 0, and ft will be 0 if t is less than 0. So that means if t is greater than equal to 0, then the threshold function will have value 1, and if t is less than 0, then the threshold function will have value 0. So we will use this threshold function to find out the output vector. So but first we have to find out the activation at each node. So let's start from the first neuron. Say the input vector which is applied is pattern A. So if we apply the pattern A to the first column of the weight matrix, then what will be the activation? Because for first neuron, it is the first column which is, coming into it. The inputs are coming into first neuron through the weights W21, W31 and W41. So we will use the first column of the weight matrix, which is 0, -3, 3, -3, to get the activation at node 1. So if we apply the first input vector, which is A, and the first input vector was 1 0 1 0. What was the first input vector? 1 0 1 0. So if this is the input vector 1 0 1 0, then what would be the activation if we find the dot product of the input vector and the first column of the weight matrix? Then what will be the dot product? If we multiply 1 with 0, 0 with -3, 1 with 3, dot product will be 1 into 0 plus 0 into -3 plus 1 into -3 plus 0 into -3. So this will come out to be 3. So then what will be F3? Then we have to apply the threshold function. So what would be F3? If you look at the threshold function, here t is greater than 0, t is 3, and since it is greater than 0, F3 would be 1. So this is the output of your first neuron. Then similarly we have to find the output for the second, third and fourth neurons. So what would be the activation for second, third and fourth neuron? For second, third and fourth neuron, we have to multiply the input, we have to find the dot product of the input vector and the second column of the weight matrix. So if we find the dot product of the input vector and the second column of the weight matrix, what do we get? -6. So that means what, when we apply the threshold function on f -6, the output will be 0. Similarly, for third neuron, we'll be multiplying the input vector with the third column. So when we multiply the input vector with the third column, the activation would be 3. So this 3 will again give us a 1 in the output. And then when the input vector is, we find the dot product of the input vector and the fourth column, what is the activation? Again it is -6. So -6 will, when we apply the threshold function, we'll get a 0. So the pattern which has been recalled is 1 0 1 0, which is same as the input pattern. So this network is able to recall the pattern which was stored in it. Similarly, if we apply the vector b, if the vector b, the value of the vector b was the vector b is 0 1 0 1. So if we apply vector b, then again we will find out the activations by finding the dot product of the vector b with first column, second column, third column and fourth column. So again for the first column we'll get activation of -6. For the second column we'll get 3, 1 0 1 0 1 will give us a 3. Again 0 1 0 1 will give us -6. 0 1 0 1 will give us a 3. So when we apply the threshold function, -6 will give us a 0, 3 will give us a 1, again 0 1. So the same pattern is recalled. So these A and B, then they are the stable patterns which the Hopfield network has stored and it is able to recall them. But the beauty of the network is that even if the input pattern is slightly corrupted or some information is missing, even then it is able to recall a stable pattern. So what that means is that, say there is some another vector C which is 0 1 0 0. If we apply this vector C 0 1 0 1 as input pattern to this Hopfield network, then what would be the activations? Again we have to find the dot product. So the dot product will give us activations as -3 for the first column. Then what it for the second, what it will be? What would be the dot product of C and the second column? 0. And C and third column, it would be minus 3, and C and fourth column, it will be 3. So when we apply the threshold function for minus 3 and minus 3, we will get 0, and for 0 we'll get a 1, because the threshold function was defined as when t is greater than equal to 0, ft would be 1. So the pattern which is being recalled is 0, 1, 0, 1. So that means pattern which is being recalled is B, right? Now the question is why it is recalling B and not A. So there is a reason for that also, because pattern A was 1 0 1 0. So when we apply a input pattern at the input of a Hopfield network, it is going to recall that pattern which is closest to it. So if you see the difference between B and C, it differs only in one element. The rest of the three elements are same. And if you see the distance between A and C, then it is different for how many elements? 3. So the difference is between A and C is 3, between B and C it is only 1. So C is most similar to B. So Hopfield network is going to recall that pattern which is most similar to the input pattern. So that is how this works. Now,
while we are recalling vector C, when we create weight matrix, we only consider vector A and B.
yeah, because that is what I am saying, that the beauty of the network is that we have trained it for two stable patterns. But even if the input is slightly noisy or incorrect, or if some information is missing, even then it will recall that pattern. So what it means is that supposing you wanted to give B only as the input pattern, but by mistake the last element became 0. So you wanted to recall B and you have been able to recall B. So that is the beauty of the network. Now, thing is, the way we have, evaluated this activation for each neuron, and then finally the output vector, we have done it synchronously. We have found for each neuron, we have multiplied the input vector with the column vector of the weight matrix and found the activation of first, second and third, fourth neuron and done it. But the if you see the structure of the network, then the output of second neuron is the input for the first neuron. So when the output of the second neuron change, the input of the first neuron also change. So it has to be done actually asynchronous. The update has to be done in a asynchronous fashion rather than a synchronous fashion, because Hopfield network is a recurrent network. If you look at your network deeply, then you will see that in the Hopfield network, we are giving an input pattern, we are determining the activation, we are applying the threshold function, we are getting an output, that output is being fed back to the input. So that means this, the manner in which we have done the evaluation of the output vector is not correct. And, it has to be updated in a asynchronous fashion. So when we say it has to be updated in a asynchronous fashion, that means once we apply a input vector and we determine the change in the output of the first neuron. So then that becomes the input vector, and then we find out the change in the output of the second neuron. So once we have determined the change in the output of the second neuron, then that becomes the input vector, and then we find out the change in the output of the third neuron. And this cycle continues till there is no change in the input and output vector. Then we say that the network has stabilized. So what that means is that the actual update will be done like this. Say we apply the input vector which is being applied is E, and the input vector now is 1 0 0 1. So if the input vector E is 1, 0, 0, 1, then we'll determine the activation for neurons 1, 2, 3 and 4 one by one, and we will change the input of the Hopfield network at each step. So you look at the first step, the input vector is 1, 0, 0, 1, and initially we set the output vector also as 1, 0, 0, 1. That is the initialization. So if the input and the output vector also, the input vector is 1, 0, 0, 1 only. And the first column of the weight matrix is 0, minus 3, 3, minus 3, right? So when we determine the dot product of this input vector and the first column of the weight vector, then you can see what are we going to get? Minus 3. If we find the dot product of 1, 0, 0, 1 and 0, minus 3, 3, minus 3, we are going to get minus 3. So minus 3, when we apply the threshold function, that means output of the first neuron is 0. So that means now the output vector at this very moment is 0, 0, 0, 1. So now this becomes the input vector in the next step. So in step 2, the input vector is 0, 0, 0, 1. Now this input vector is applied to the second column of the weight matrix, which is minus 3, 0, minus 3, 3. So when it is applied to the second column of the weight matrix, you can see when we find the dot product is going to be 3. So now when we apply the activation function, the output of the second neuron is going to be 1. So now the output vector at this moment is 0, 1, 0, 1. So this becomes the input vector in the next step. So now we find the activation for the third neuron by taking third column of the weight matrix, which is 3, minus 3, 0, minus 3. So now your activation will be minus 6 and the output will be 0. So now this output vector becomes the input vector in the next step, which is again 0, 1, 0, 1. And we find out the activation for the fourth neuron by taking into account the fourth column of the weight matrix, which is minus 3, 3, minus 3, 0. So now your activation is 3, right? So for 3, when we apply the threshold function, output is going to be 1. So again, you see we repeat this now. In the next cycle, 0, 1, 0, 1 is the input vector. We find out the output of the first neuron by taking first column of the weight matrix. So in the next cycle, when we find out the activations and the outputs of first, second, third, fourth neuron, you see the input and the output vector in steps 5, 6, 7, 8 remain the same. So for one complete sweep, the input and output vector have not changed. So that means the pattern being recalled is 0, 1, 0, 1, which is B. Now, if we followed the earlier method where we were, changing the output synchronously, then look at what will happen. If we take E as an input vector, 1, 0, 0, 1, and we take the weight matrix and synchronously determine the output vector, then output vector will come out to be 0, 1, 1, 0. Now this output vector becomes the input vector. So when this becomes the input vector, the output vector will be E. So in the next cycle, this output vector will be the input vector. Then your output vector will be this. So that means the network is basically oscillating between these two states. So that will never happen actually. Why? Because the outputs are actually updated asynchronously rather than synchronously. So we have to take into account that the outputs have to be updated asynchronously. Now let's see how Hopfield network is used for pattern recognition. So when we use patterns, we will choose some grid size. So if we choose a grid size of 5 by 7, then pattern would be represented on a grid size of 5 by 7. So that means we will require 35 neurons, right? Here in this example, we are choosing a grid size of 3 by 3. So that means there will be 9 neurons in the Hopfield network, and the portion which is dark is represented as 1 and which is light is represented as -1. So you can see that the bipolar vectors for the pattern plus and minus, these are two patterns, plus and minus. So what would be the pattern for plus? How many elements would be there? In 9. 9 elements would be there. So if we have to read the pattern for plus, it would be, since first element of the grid is blank, it would be -1. Second is filled, so it will be 1. And third would be -1. Then for the next row, it would be -1, 1, 1, 1. And for the last row, it would be -1, 1, -1. So that would be the pattern C plus for plus. And for minus sign, the pattern C minus would be -1, -1, -1 for first row, 1, 1, 1 for second row, and -1, -1, -1 for the third row. So if these are the two input patterns, then we have to find out the weight matrix by following the same procedure that we had done earlier. So for the first pattern, we will take the transpose and multiply. For the second pattern also, we will take the transpose and multiply, and then we will add. So addition will give us this weight matrix. So now you can see if this is the weight matrix with you, and if the input pattern is plus, then what would be the activations for C plus? If this is the weight matrix, and when we apply the input pattern for say plus, then what would be the activation for the first neuron? For first neuron, we'll consider the C plus pattern and first column. So what will be the value? If you take the C plus pattern, it is -1, 1, -1. So -1, 1, -1, if we take the first three elements of the first column, will give you a -2, right? Then next is 1, 1, 1. So again we'll get -2, -2, -2. That is, then you have now -8. Then next is, last row is again -1, 1 and -1. So again you will get -2, -2. So activation is -12. So you can see that if your input vector is C plus, then activations for the 9 neurons are going to be -12, 2, -12, then 12, 12, 12, and -12, 12, 2, and -12. So if these are the activations, and if we use the threshold function, which is given as fx is 1 if x is greater than 0, and -1 if x is less than equal to 0. So that means if x is 0, the output will be -1. So then what would be the output vector? If we apply this threshold function, if the input pattern is C plus, first element is -12. So when we apply the threshold function to -12, we will get out -1. Function value is -1 if x is less than equal to 0. So since x is -12, the output function will be -1. For -12, we will get -1. What will we get for 2? 2 is since greater than 0, so we will get a 1. So next value would be 1. Then next element is, next activation is -12 for the third neuron. So what would be the output? -1. The output will be again -1. Now the next three activations are 12, 12, 12. So the output will be 1, 1, 1. Then it is again -12, -2, -12, 2, and -12. So for -12, the output will be -1. For 2, it will be 0. And for -12, it will be -1. So you can see that this is the pattern for C plus. So we gave C plus as the input pattern and we could recall it. Similarly, if we give C minus as the input pattern, we will recall C minus. So, but what patterns we have saved, the network is able to recall those patterns, right? But the beauty is that even if the patterns are slightly corrupted, even then the correct patterns would be recalled. So let's see, say this is the input pattern. Now this pattern is a corrupted pattern of C minus. In C minus, the first and the third row were blank and the second row all the elements were filled. So now for this pattern, the bipolar vector that we are going to get is 1, minus 1 for the first row. For the second row, we will get 1, 1, 1. And for the third row, we will get minus 1, minus 1, minus 1. So now, if this is your input pattern, then what would be the activation? So activation, you see it comes out to be minus 12, minus 2, minus 8. So minus 12, minus 2, minus 8 will give you what output? If the activation is minus 12, the output will be minus 1. Again, the activation is minus 2, so output will be minus 1. Again, activation is minus 8, so output will be minus 1. Now, next three activations are 4, 4, 4. So, for that, the output will be 1, 1, 1. And then the next three activations are minus 8, minus 2, minus 8. For that, again, your output will be minus 1, minus 1, minus 1. So, which pattern is this? C minus. So the input was a slightly corrupted pattern, but we could recall the minus pattern. So, the pattern which it was supposed to recall, the network is able to recall. And in addition to that, it is able to recall some other similar patterns also. Like you see the pattern in figure 6. We have the corners which are filled. So this is not a plus or minus sign. But what is this? If we have to write the vector for this pattern, what that vector would be? If we have to write down the vector for this pattern, what that vector would be? For first cell, we'll write a 1, then minus 1, 1, minus 1, minus 1, minus 1, then 1, minus 1, 1. So these are the 9 elements of this pattern. Now, if we find out the activations for this pattern, then activations for this pattern would be 12, minus 2, 12. You have to find out the dot product of this vector with each column. So the activations come out to be 12, minus 2, 12, minus 4, minus 4, minus 4, and 12, minus 2, 12. So if these are the activations, what will be the output vector? For 12, the output will be 1. For minus 2, it will be minus 1. For 12, it will be 1. For minus 4, it will be minus 1, then minus 1, then minus 1. For 12, it will be 1, then again minus 1 and 1. So you see the network is able to even recall this pattern. Although we did not train it for this pattern, still it could recall this pattern. And similarly, if we go back and see this, in figure 7, I have shown a partly lost pattern. So if we compare figure 6 and 7, the last two elements of the last row are missing. So then this vector would be 1, minus 1, 1, and then all minus 1s. So if this is your input vector, then the output vector which is recalled is 1, minus 1, 1, minus 1, minus 1, minus 1, 1, minus 1, 1. So that vector is basically which is vector B. So it is able to recall the pattern in figure 6. So that is the beauty of the network.
One question. So we generate rate matrix by using vectors C plus and C minus. We are able to recall other patterns also.
A few other patterns. Which are close to these patterns.
Okay. Most of the time we will get C plus, either C plus or C minus.
C minus, because these are the two stable patterns, because we have found out the weight matrix using these two patterns.
Okay. But if we train the network with 10 or 15 patterns,
then it will be able to recall some close patterns. See, one is your training set, other is your test set. So you have trained the network using say 15 pairs, 15 vectors. But then it is not that the network will recall only those 15 vectors. It is able to recall some other vectors also, which are close to the vectors which we have used to train the network. So another application of field network is that it can be used for analog to digital conversion. So say we want to make a 4-bit analog to digital converter. So analog to digital converter means that the input will be analog and the output would be digital. So in this graph, basically I have shown the input analog voltage along x-axis and the output digital voltage along y-axis. So what it means is that when your input voltage is 0 volts, the output should be 0, 0, 0, 0. When the input voltage is 1 volts, then output voltage should be 0, 0, 0, 1. And similarly for 2 it should be 0, 0, 1, 0. And for 15 it will be 1, 1, 1, 1. So we can use a Hopfield network for A to D conversion. And how we do it is, we use operational amplifiers as neurons. So you see this network which is built from operational amplifiers. Now Hopfield network, you have already seen the output of each neuron is connected to the input of every other neuron. So here these 4 operational amplifiers are neurons, and each operational amplifier has 2 outputs. One is inverting output, other is the non-inverting output. Here we have shown all the inverting outputs are being fed back to the input. So you see the first inverting output V0, when it is fed back to the input, it is being fed back to the second, third and fourth neuron, but it is not being fed back to the first neuron. Similarly, when we are feeding back the output of the second op-amp, which is minus V1, it is being fed back to first op-amp, third op-amp and fourth op-amp, but not to the second op-amp. Similarly, the output of the third op-amp, which is minus V2, is being fed back to the first op-amp, second op-amp and the fourth op-amp. And the output of the fourth op-amp, which is minus V3, is being fed back to first, second and third op-amp, and it is not being fed back to the fourth op-amp. So we have followed the structure of a Hopfield network, and then the input is being applied to input terminal of all the operational amplifiers. Here we have not used the inverting terminal of the op-amp, but we will use both inverting as well as non-inverting terminals. And wherever the weight is negative, we will use the inverting terminal. Wherever the weight is positive, we will use the non-inverting terminal. But that also means that for a op-amp, either we will use the inverting terminal or we will use the non-inverting terminal. So depending upon the weight, if the weight is negative, we will use inverting terminal so that we get the minus sign when we are writing our mathematical equations. And when we have a positive weight, then we will use the non-inverting terminal. So by this architecture, when we apply the analog input, we can determine the resistances like that we get the digital output. So we can use Hopfield network for analog to digital conversion also, besides memorizing the patterns. Now we come to heteroassociative memory, because you have seen that Hopfield network is auto-associative. The input pattern and the output pattern being recalled are same. Now in the heteroassociative memory, we will have two layers. So we have field A and field B. We have two layers of neurons, and in this, in each layer, every neuron in a particular layer is connected to every neuron in the other layer. So you can see in field A, the first neuron is connected to both the neurons in field B. Similarly, the second neuron in field A is connected to both the neurons in field B. Then third neuron in field A is also connected to both the neurons in field B. And the reverse is also true. Every neuron in field B is connected to every neuron in the field A. So if you look at the first neuron in field B, it is connected to all the three neurons in field A. Similarly, the second neuron in field B is connected to all the neurons in field A. So, if we look at first neuron in field A and first neuron in field B, we have two weights between them, W11. One is from field A to B, the other is from B to A. So then similarly we have W21, which is connecting first neuron in field A to second neuron in field B. Then second neuron in field B is also connected to first neuron in field A via W12. So, the weight matrices between field A and B and A, the weights are same. W12, W21, W32, W23, they are same. So what is done is, to find out the weight matrix, we find out the weight matrix say between field A and B. So we find out the weight matrix between field A and B, and then we take transpose of that weight matrix. That becomes the weight matrix from B to A. So when we are to find the weight matrices between A and B and A, we only need to find one weight matrix, and we take transpose of that weight matrix. That becomes the weight matrix for the reverse situation. So the method of finding the weight matrices remains the same. We will take input-output vector pairs one by one, and for each pair we will find the contribution of each pair to the weight matrix. Then we'll add the contribution of all the input-output pairs to get the final weight matrix. So let's take an example where we take two patterns. So two patterns means two pairs basically. Two pairs means two associations. One input-output vector and second input-output vector. So first input-output vector is x1, y1. So we want this heteroassociative memory to memorize the association between x1 and y1. That is one input-output vector pair. And the other input-output vector pair is x2, y2. So x1 is 1, 0, 0, 1 and y1 is 0, 1, 1. Similarly, x2 is 0, 1, 1, 0 and y2 is 1, 0, 1. So these are the two input-output vector pairs or two associations that we want the bidirectional associative memory to memorize. So to get the weight matrix, we again have to change the binary vectors into bipolar vectors. So x1 will become 1, minus 1, minus 1, 1. y1 will become minus 1, 1, 1. x2 will become minus 1, 1, 1, minus 1. And y2 will become 1, minus 1, 1. So in Hopfield network, what we were doing, the input vector was there in the binary form. We converted into its bipolar form. We took the transpose and then we multiplied the column vector with the row vector. There we did like that because the input and output vector was same. Now we have different input and output vectors. So what we will do is we will take transpose of the input vector and multiply it with the output vector. So to determine the weight matrix, we take transpose of x1. Transpose of x1 will be a column vector 1, minus 1, minus 1, 1. It is to be multiplied with the output vector y1, which is minus 1, 1, 1. So that will be the contribution of x1, y1 to the weight matrix. We have to add this to the contribution of x2, y2 to the weight matrix. So to find out the contribution of x2, y2 to the weight matrix, we have to repeat this procedure. We have to take transpose of x2. Transpose of x2 would be minus 1, 1, 1, minus 1, and then we have to multiply it with the output vector y2, which in the bipolar form is 1, minus 1, 1. So then we have to multiply, column vector with each element in the row, and then we have to add. So when we multiply 1, minus 1, minus 1, 1, which is a column vector with minus 1, we will get the first column of the first matrix. When we multiply it with 1, we get the second column. When we multiply it with 1, we get the third column. Then similarly for x2, y2, when we multiply the column vector with the first element 1, we get the first column of the weight matrix. Then we multiply it with minus 1 to get the second column. We again multiply it with the third element to get the third column. And finally we add. So when we add, the weight matrix is minus 2, 2, 0, 2, minus 2, 0, 2, minus 2, 0, and minus 2, 2, 0. So when we are saying that these are our input-output vectors, what does it mean? How many neurons in field A and how many neurons in field B? The input, huh, 3. So we will have 4 neurons in field A and 3 in field B, and the weight matrix between A and B would be given like this. Then we have to find out the weight matrix between B and A also. So that we will find by just simply taking transpose of this weight matrix. So when we take transpose of this weight matrix, we get WT. So again, we can multiply the elements of these weight matrices by any scalar, and if we multiply the elements of these weight matrices by any scalar, then we can change the value from 2 to 3 or 4 and like that. So once we have found out the weight matrices, next step is to choose the thresholding function, because the weight matrices will help us in finding out the activation of each neuron, and from the activation function we have to find out the output of the neuron, and output of the neuron will be found by applying the thresholding function. So now we have defined the threshold functions for elements in field B as well as in A, and the thresholding function is that for the neurons in field B and in cycle J plus 1, the output of the neuron will be 1 if the activation is greater than 0. It will be same as the previous value if the activation is 0, and it will be 0 if the activation is less than 0. So now we have defined 3 things. The output of the neuron will be 1 if activation is more than 0. It will be 0 if the activation is less than 0. But if the activation is 0, then it will remain unchanged. Whatever it was, it will remain the same. Similarly for neurons in field A, also we define the activation function in the same way. Activation, the thresholding function in cycle J plus 1 would be 1 if the activation is more than 0, would be 0 if the activation is less than 0, and will remain unchanged if the activation is 0. So Xi and Yj, they are basically the activations of neurons I and J in the input and output layer in field A and B. And the output Bj at time t refers to the output in the cycle t, and at t plus 1 it refers to the output in the cycle t plus 1. So now, using this weight matrix and thresholding function, if we take the input vector x1 as 1, 0, 0, 1, if it is represented to the input neurons, what would be the activations of the input neurons? We have to find out the dot product of the input vector, and first column of the weight matrix we have to take. You see there are 3 columns of the weight matrix. So first column will give us the first activation function. So the vector x1 is being taken as 1, 0, 0, 1, right? So when we use this vector and apply it to the first column of the weight matrix, what activations we will get?
minus 2, minus plus minus 2.
1, 0, 0, 1. So 1, 0, 0, 1 applied to minus 2, which will give us minus 4. So we will get minus 4. When we apply it to the second column, then we will get, second column will give us,
0.
no, the second column, the weights are 2, minus 2, minus 2, 2. When we take its dot product with 1, 0, 0, 1, we will get 4. So activation is 4. And for the last column, since all elements are 0, the activation is going to be 0. So you see here that when we apply x1 as the input pattern, the activations for the neurons in the output layer would be minus 4, 4, 0. So then what will be the output? For minus 4 activation, what will be the output? 0. For 4 it will be 1. And for 0 it will be what it was previously. And what it was previously? 1. So this will be 1. So this is your y1. So we applied x1 as the input pattern and we get y1 as the output pattern. Similarly, if we apply y1 at field B, so y1 is this. Y1 is 0, 1, 1. So if we apply y1 at field B, then the weight matrix which will be used is WT, right? So when we use WT, what will be the activations? We have to apply y1 to the first column to get the first activation. So what will that be? When the transpose of the weight matrix, you can see there it is minus 2, 2, 0. So when we multiply this with minus 2, 2, so we will get 2. Then when we use the second column, then we get minus 2. Then we use the third column and we get minus 2. Then we use the fourth column and we get 2. So these are the activations. So now when we apply thresholding, 2 will give us 1, minus 2 will give us 0, minus 2 will give us 0, and 2 will give us 1. So the pattern being recalled is x1, right? So it is bidirectional. x1 input pattern, y1 the output pattern. And if we apply y1 as the input pattern at the output layer, we get the x1 at the input layer. So this is how it works. It memorizes the associations and it memorizes the associations both way. So we can test it for x2 and y2 also. So if we test it for x2 and y2, x2 and y2 were, x2 was given to be 0, 1, 1, 0 and y2 was 1, 0, 1. So if we have to test it for x2 and y2, again if x2 is the input pattern, then we will use the weight matrix W. So the activations would be 0, 1, 1, 0 will give us 4, right? First column will give us 4, second column will give us -4, and third column will give us 0. So that means 4 will give us a 1, -4 will give us a 0. This is 0, so it will remain what it was, so it will remain 1. So y2 has been recalled. Similarly, if we apply y2 at the output layer, the input layer will recall x2. So both ways it will work. Now, because it will remain same. Y2 is already in the previous cycle, it was 1, so it will remain 1. Because we are only considering present cycle, right? So, but say the network has, when we were training the network, it is already memorized like this, right? So previously it will, recall the previous value. So now supposing the input vector is slightly corrupted, say x1 is modified to, say we modify x1. Say x1 is modified to 1, 0, 1, 1. Then what will happen? So if we modify x1, then we have to modify the weight matrix also. So when we modify the weight matrix, we take bipolar vector 1, -1, 1, 1 and we find out the weight matrix. And we take the transpose to find out the weight matrix between field B and A. So now the input patterns are x1 is 1, 0, 1, 1 and y1 is 0, 1, 1 and x2 is 0, 1, 1, 0 and y2 is 1, 0, 1. So, if we now we apply the same logic, then when we apply x1 as the input vector, y1 will be the output, and when we apply x2 as the input vector, y2 will be the output. When we apply y1 as the input, y1 at the field B, we will get x1 at field A. When we apply y2 at field B, we will get x2 at field A. So, we can change the input and output vector pairs and find out the weight matrices and, test. We can apply the input vector, we'll be able to recall the output vector. This method will work. No, once the network is trained, then it is trained. So if a noisy pattern comes, it will recall that. And bidirectional associative memories, since it memorizes the association between two patterns, it has wide number of applications. It can be used for predictions. It can be used for prediction of avalanches. In fact, there are softwares which have been developed based on bidirectional associative memories, which help school children. Like, we have Bohr's table for elements. So we have the abbreviation for element and its mass number. So it can memorize the association between the abbreviation and the mass number. So if abbreviation is the input, the output will be the mass number. So it can memorize associations and can be used for a number of applications. So then last part of this associative memories is your fuzzy associative memory. So we not only have, binary or bipolar associative memory, we can also have fuzzy associative memory. So the structure of fuzzy associative memory will be same as that of bidirectional associative memory. We will have two layers of neurons and in every neuron in a layer would be connected to every other neuron in the next layer. And the connections are between layer 1 and 2, layer A and B, as well as between B and A. So we can find out the weight matrix between A and B and take transpose of that to find matrix between B and A. The only thing is that how to do multiplication and addition, because now you will not have binary numbers, rather you will have the membership grades. So in the decimal system, you will have the numbers. So we have to use max min composition. So wherever multiplication is to be done, we will use minimum of the two, and wherever addition is to be done, we will use maximum of the two. So say we have two fuzzy vectors. So the first fuzzy vector is 0.3, 0.7, 0.4, 0.2, and it is associated with the other fuzzy vector, which is 0.4, 0.3, 0.9. So the method of determining the weight matrix will remain the same. We have to take transpose of the input vector. So it becomes a column vector, 0.3, 0.7, 0.4, 0.2, and the other vector remains a row vector. Now we have to find out, now we have to multiply this column vector with each element of the row vector. So when we multiply the column vector with 0.4, then we have to find minimum of 0.3, 0.4, minimum of 0.7, 0.4, minimum of 0.4, 0.4, minimum of 0.2, 0.4. Then for the second element, minimum of 0.3, 0.3, minimum of 0.7, 0.3, minimum of 0.4, 0.3, minimum of 0.2, 0.3. Then we come to the last element in the row vector. So we have to find out minimum of 0.3, 0.9, 0.7, 0.9, 0.4, 0.9, 0.2, 0.9. So when we take the minimum, the weight matrix will be 0.3, 0.3, 0.3, 0.4, 0.3, 0.7, 0.4, 0.3, 0.4, 0.2, 0.2, 0.2. So this is your weight matrix between field A and B. And between B and A, we can take the transpose and find out. So when the input vector is 0.3, 0.7, 0.4, 0.2, then we have to find the, first we have to find the dot product, we have to, multiply each element with the corresponding element in the first column, then second column, then third column, and then add. So when we multiply, we have to, when we multiply, so, when we multiply the vector 0.7, 0.3, 0.7, 0.4, 0.2 with the first column, we have to find minimum of 0.3, 0.3, minimum of 0.7, 0.4, minimum of 0.4, 0.4, minimum of 0.2, 0.2. And then we have to add. So addition will be done by finding maximum. So maximum, so we have to find minimum and then maximum of the minimum. So when we find minimum, we get 0.3, 0.4, 0.4, 0.2, and when we find maximum of that, it will be 0.4. So so B1 is coming out to be 0.4. Similarly, we can find B2 and B3. They will come out to be 0.3 and 0.7. So that means the pattern which is being recalled is 0.4, 0.3, 0.7 and not 0.3, 0.4, 0.3, 0.9. But it is very close to the pattern which we want. So in the opposite direction, if 0.4, 0.3, 0.7 is the input vector for field B, then output vector for field A would be 0.3, 0.7, 0.4, 0.2. So, again, the same resonance is maintained between the input and the output vectors. So it is able to recall the association between the input and the output vectors.